Hey guys, this is the Chem 1 lecture of Unit 9, Moles with Mole Calculations. How do you count the number of atoms in a compound? So when we're asking about the word atoms, we mean like single elements. So SO3, or sulfur trioxide, has 1 sulfur and 3 oxygens, and so that has a total of 4 atoms. The next example, ammonium sulfate. This 2 on the outside would be distributed. And once again, if we're asking you about atoms, we want you to break down into specific elements. So distributed, we have 2 nitrogens, 8 hydrogens, 1 sulfur, and 4 oxygens, which would make a total of 15 atoms. And then lastly, iron 3 hydroxide. We would first have to write the formula. So the Roman numeral is the charge of the metal. Hydroxide is a polyatomic found on the back. And so for our charges to equal 0, we're going to need 3 hydroxides for it to be balanced. And then break down by element. Iron, oxygen, and hydrogen. We have 1 iron. If we distribute the 3, we have 3 oxygens and 3 hydrogens. So 6 plus 1 is 7 atoms. Another way we could ask you to count is the number of ions. And so the difference between atoms, which we talked about first, and ions is polyatomics, things that are found on the back, stay together. So I'm going to make a little note. Polyatomics stay together. You count them as 1 unit. So for example, in ammonium sulfate, we have the ion ammonium, NH4. We're keeping that polyatomic together and simply counting that we have 2 ammonium ions. And SO4 is an implied that there's 1 of them. So another polyatomic that stays grouped together, and we have 1 sulfate. So add those up, and we have a total of 3 ions. So our vocab word has changed, and we're using ions. Iron 3 hydroxide, we wrote this formula up above. So we're going to count ions. Iron is an ion, and then hydroxide is a polyatomic ion. So we have 1 iron ion, and we have 3 hydroxide ions. And so we have a total of 4 ions. Atoms are really small, so is it realistic to count individual atoms? Meaning, if you think about like a water bottle full of water molecules, it's not really realistic for us to actually count individually because there's millions upon millions upon millions of water molecules inside just even a glass of water. And so chemists use a counting unit called the mole. What do we mean by the mole? Well, let's start with what we don't mean. We don't mean the animal, the mole, and we don't mean the mole on a person's face. What we do mean is that a mole is a word that represents a set number. So for example, if you hear the word dozen, we all can agree that a dozen means you have 12 things. A gross means you have 144 things. A ream means you have 500 things. If you have a pair of something, you have 2 things. And so what we're building into your vocab is if you have a mole of something, you have 6.02 times 10 to the 23rd or sextillion things. A very, 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 very big number. The scientist that's credited for coming up with this number, his name is Avogadro. So sometimes the mole is referred to as Avogadro's number. And so in scientific notation, if we make our coefficient between 1 and 0, it's 6.02 times 10 to the 23rd. Fun little fact is that there's actually like a National Mole Day, and it is on October, the 10th month. 23rd, so October 23rd, and it runs from 6:02 a.m. to 6:02 p.m., and they have just a lot of puns on moles, like rock and mole and stuff like that. In some of your teachers' classrooms, you might see some stuffed mole animals that are kind of just playing on the chemist's quantity called the mole. So if you have 1 mole of pennies, you would have 6.02 times 10 to the 23rd pennies. And there's a fun TED Ed video that says how big is a mole that gives you really cool facts that, like, this one says, like, if you spend $1 million a second from 0 to 99, you would still have 99.9% of your wealth if you had a mole of pennies. So that is a ton of money. If you had a mole of aluminum, you'd have 6.02 times 10 to the 23rd pieces of aluminum. If you had a mole of oxygen, you would have 6.02 times 10 to the 23rd particles of oxygen. So the mole is a consistent number, 6.02 times 10 to the 23rd. All right, so let's see if we can apply this a little bit. If you had 1 mole of barium nitrite, so we'd first have to write out our formula. And it says, how many moles of barium ions do you have? Well, in your formula, there's only 1 barium. And so if you had a mole of it, it would break up, like if this thing dissolved into its ions of barium and nitrite, you would have 1 mole of barium, but you would have double the amount of the nitrite ions. So I've heard it kind of explained like this, that if you think about a pen that has like 2 caps, and let's say you have 12 pens, a dozen pens, if this were to split up into its pieces of bodies and like caps, you would have 12 bodies of the pen, but you would have 24 caps. So when we break a molecule down, you can have more than just 1 mole of something. But because we only had 1 barium, we have 1 mole, but we had 2 nitrite ions, and that can equivalent into 2 nitrite moles. Okay, moles of barium atoms would be the same. You still have 1 mole. So notice our vocab just shifted to atoms, and when you see atoms, you're always breaking it down to the element. So there's only 1 barium in our formula, so if you had 1 mole of it, you'd have 1 mole of barium. For nitrogen, though, you would have to distribute the 2 in your formula, and so because you have 2 nitrogens, if you had a mole of it, you'd have 2 moles of nitrogen. And then oxygen, you'd have 4 moles of oxygen. That would be the most pieces. And now that you know how many moles are in your formula, you could then use Avogadro's number to figure out literally how many atoms do we have, literally how many pieces do we have. So if you have 1 mole of barium, then you have exactly 6.02 times 10 to the 23rd atoms of barium. If you had 2 moles of nitrogen, you would have 2 times the mole number, which would equate to 1.204 times 10 to the 24th atoms of nitrogen. And then if you add 4 moles of oxygen, well, we know that 1 mole is 6.02, so we would just quadruple the mole number, also referred to as Avogadro's number, and you'd have 2.41 times 10 to the 24th atoms of specifically oxygen. Okay, we need to be clear on our vocab. And so some of the words that we're going to be using this unit are atoms and molecules. So we're saying that an atom has no bonds in it. It's a substance in its elemental form. This does not include diatomics. We're calling things molecules for atoms that have a chemical bond. They're chemically combined, which includes diatomics. Diatomics are the 7 elements I bring clay for our new house. So let's go through this chart using this vocab and what we've been talking about in terms of counting. So here I have sodium sulfide. The particle type is going to be called a molecule because I have 2 elements chemically combined. The number of atoms, so remember atoms I want broken down by element. So I have 2 NAs and an S, so I have 3 total atoms. And then ions, remember polyatomics stay together. Just gonna write poly stay. Now in this example there is no polyatomic. Because this is an ionic bond, a metal and a non-metal, then it will have an equal number of ions. Like if this were to dissolve in water, we'd have 2 sodium ions and 1 sulfur ion with a net charge of 0. So remember, an ion is just a charged particle. So we would have 3 charged particles in this first example. Okay, let's try another one. Helium. So that particle type is an atom. It's not in a bond with anybody else. There is only 1 helium atom, and helium is not an ion. Remember, to be an ion, it first has to be an ionic bond, which is between a metal and a non-metal, typically something positive and negative. All right, third example is nitrogen, but notice that there's 2 of them, so we're going to call this a molecule. And there's 2 atoms, so atoms is like single element. And then there will be no ions because this is a covalent bond, 2 nonmetals. Fourth example is barium phosphate. So right off the bat I noticed that this is ionic. There's a metal present and a polyatomic. So the particle type is definitely a molecule. So molecule is just anything with more than 2 elements. Atom-wise, we're going to have to break this down. So I'm going to give us a little more room. And if they're asking for atoms, it breaks down by element. So we have barium, phosphorus, and oxygen. We have 3 bariums. If we distribute that outer 2, we have 2 phosphorus and 8. So we have a total of 13 atoms. And then ions, do you remember how we count it differently? You keep the phosphate ion together. So if I were to redo this, I would keep PO4 together. I have 3 barium ions, and I have 2 phosphate ions, so I have a total of 5 ions. And then one more, it's called ammonium sulfite. And I'm also noticing that this is ionic. Not off the bat, because there's all nonmetals, but NH4 actually carries a positive charge, and so it's a cation, and sulfite, SO3, carries a -2 charge, and so that positive-negative creates an ionic bond. So the particle is going to be a molecule. Now, it wants to know how many atoms are in ammonium sulfite. We're going to have to make a list of all the elements in ammonium sulfite, which we have nitrogen, hydrogen, sulfur, and oxygen. If we distribute the 2, we have 2 nitrogens, 8 hydrogens, 1 sulfur, 3 oxygens, and that ends up being 14. So I'm kind of running out of room up here, but there's 14 atoms. But then ions, if there's polyatomics, you keep them grouped together. And in this case, there's 2 polyatomics. There's the polyatomic ion ammonium, and there's the polyatomic ion sulfite, and that was a 2-to-1 ratio. So there's a kind of understood, unseen parentheses with a 1. So there's a total of 3 ions in this molecule. And we're going to put it all together. It's going to make more sense when we do some math, but you're going to really have to watch out for, are they asking about molecules, atoms, ions? So there's a little bit of vocab at the beginning of this unit. So this is going to be a really helpful this is going to be a really helpful tool or map for Unit 9. We're going to be in the highlighted areas today, but we're introducing this concept of a mole. So this chemical or this chemistry counting number. Today we're going to focus on the fact that if you have 1 mole of something, you have Avogadro's number. 6.02 times 10 to the 23rd things. Now, if those things happen to be a molecule, so there's more than one element present, then we can break them into ions or atoms. And so this is going to be a helpful roadmap as we start to bring in dimensional analysis, that you might have a 2-step problem because they give you, hey, you have 5 moles of something and I want to know how many ions you would have. We'd first have to figure out how many molecules and then break down the molecule. Or vice versa, you have moles, you figure out how many molecules you have, and then you want to know how many atoms you have. And so this is just a nice roadmap to know where we're headed. And over the next few days, we'll also bring in how mole relates to mass and volume. But today we're going to focus on the particle side. Okay, so we're going to take on some mole calculations. So dimensional analysis is back. So if it was your favorite, then get ready. You got a lot in this unit. If it was not your favorite, this is a second chance to get better at dimensional analysis. So example number 1 says, how many atoms of copper are in 2.5 moles of copper? So back in Unit 1, when we were teaching you this, you always write what you're given, 2.5 moles. And then the unit you start with needs to immediately carry down because this is a division symbol, and so we need moles to cancel out. And so then we have to be like, oh my gosh, what is a mole? Well, conveniently today we only know one thing. 1 mole is the same thing as having 6.02 times 10 to the 23rd molecules or atoms. Because we're dealing with just the element copper, we're going to say that we have atoms. We don't have a molecule. It is literally just Cu. And then if you remember, we get our final answer by multiplying the top and dividing by the bottom. In this case, the bottom's 1. So 2.5 times Avogadro's number gives you a answer of 1.5 times 10 to the 24th atoms of copper. Now I went ahead and rounded to 2 significant figures because what I started with had 2 significant figures. And then remember, we encourage you in your calculator for the times 10 raised to switch it to that E function. And you do that by hitting the second button on the calculator and the comma button that's above the 7. And that replaces times 10 raised. All right, let's try another one. Determine the number of moles in 6.1 times 10 to the 24th molecules of fluorine. So I'm going to write what I'm given. 6.1 times 10 to the 24th molecules of fluorine. So they've hinted that fluorine is a diatomic by calling it a molecule. It means there's more than one of something. And I want to know how many moles this is. And so molecules has to drop down, and I have a relationship starting today between molecules and moles. I know if you have 1 mole of anything, you have 6.02 times 10 to the 23rd things. Our things in this case were molecules. And so I would multiply the top, I would divide by the bottom, and I would have 10 moles of fluorine molecules. All right, let's try another example. How many chloride ions are in 4.79 moles of barium chloride? And this one's going to be different. It's going to actually have a couple more steps due to some of the vocab words. 4.79 moles of barium chloride, BaCl2, That's because barium is a +2 ion, chlorine's a -1, so we need another chlorine for our charges to balance, become neutral. So I'm currently in moles, which if you have a mole map in front of you, you're dead center, and they want to take it to ions. So if you're looking at your map, you can see this is going to be a two-step problem. The first step is going to figure out, well, how many molecules do you have? And then when those molecules break up into ions, how many ions do you have? So our first step will be converting out of moles into molecules. Now just be careful how you're abbreviating everything so you're not confusing them. So if I have 1 mole of barium chloride, I know I have 6.02 times 10 to the 23rd molecules of barium chloride. But they want to go beyond molecules. They want to get to ions. All right, and they specifically want chloride ions. And so I'm going to have to look at 1 molecule of BaCl2. How many chlorine ions are there? There would be 2 chlorine ions. If they would have asked me about barium, there would have been only 1. And then, as always, multiply the top, 4.79 times 6.02 times 10 to the 23rd times 2 divided by 1, and you will get 5.77 times 10 to the 24th chloride ions. All right, last example for today. If a sample has 7.06 times 10 to the 22nd atoms of oxygen, how many moles of aluminum nitrate does it contain? So we always start with what we're given, 7.06 times 10 to the 22nd atoms of oxygen, and we're headed to moles of aluminum nitrate. So we are actually starting at the bottom of this map because we're specifically in the element oxygen, and we want to get to moles. And so with our map, it's going to be a two-step process. We first have to convert atoms of oxygen into just how many total molecules we have, and then from there we can convert into moles. So how many atoms of oxygen are in 1 molecule of aluminum nitrate? So if we do 3 times 3, there's 9 atoms of specifically oxygen if you had 1 molecule of aluminum nitrate. That converts us back into the whole thing, into aluminum nitrate. And then we want to convert molecules into moles. And if you've caught the pattern, the mole gets the 1. If you have 1 mole of anything, you have 6.02 times 10 to the 23rd molecules of aluminum nitrate. So then I'd multiply the top, 7.06 times 10 to the 22nd times 1, divide by 9, divide by 6.02 E23. That's my personal way. Otherwise, multiply the top, multiply the bottom, and then divide the 2. And you should get an answer of 0.0130 moles. And let's be clear, we have moles of aluminum nitrate. Now, we're not necessarily going to take off in this unit if you don't write what substance you're in, but when we get to unit 11, it's really important, and we will take off if we don't know what substance you're in. So now that you know what a mole is, we will let the mole jokes begin. Got mole problems? Call Avogadro, 6.02-1023. Please, please, please do your practice on this, and see you next time.